Hi class, we are on 11C, so here we go. This is one of my favorite lessons, but we're going to make it as short as possible, and we're dealing with proportion and the golden ratio. So what you're looking at is a great showcase of the golden ratio. And Johannes Kepler said in 1571, or that's when he was born. He was born 1571, died 1630. So this was a long time ago. It's during that golden age of mathematics, pretty much when mathematics was being developed widely. But he said geometry has two great treasures. One is the theorem of Pythagoras, which we know to be a squared plus b squared equals c squared, making a right triangle. The other, division of a line into extreme and mean ratio. The first we may compare to gold. The second we may name a precious jewel. And he is right. The golden ratio is prevalent throughout a lot of things in our world, and including our bodies. Our bodies have a lot of golden ratio aspects in them. Kepler's statement about the division of a line into an extreme and mean ratio describes one of the very oldest principles of proportion, and that is the golden ratio. And you can see it here. This is they call it height here, I would call it base, but your height, the long side, and then this height is the short side. I mean, they're almost roughly the same, but not quite. But if you take the greater length and divide by the shorter length, then what you get is this little symbol here, and it's the golden ratio, and it's 1.618, 1.62. So when scholars ask the following question, how can a line segment be divided into two pieces that have the most appeal and the most balance? And the answer is the golden ratio. So here's a picture of it. You see this line, it's divided right at a point where if I took this length right here and divided by this length, then I should get big L plus 1 divided by big L. And when divided out, I don't want to go into this because it's really unnecessary. Just understand that it's a 1 plus radical 5 over 2, or 1.61803, or 1.62 is what you'll most prevalently use in your homework, or 8 divided by 5. Any line segment divided into two pieces according to the golden ratio, the ratio of the long piece to the short piece is approximately 1.61803. All right, the golden ratio. So I used to, when I would teach this in my in classes, I love to get out some rulers and put everybody in partners, and we'd see who has the perfect body. And you could do a couple of things. You could do it with your nose. You can measure the width, the height, the longest width, the widest width of your nose, and the length of your nose, and see if you get 1.618 or something close. Your width of your face, your length of your face is another. The most pleasing, or whatever people look at and say, oh, the most pleasing faces seem to have that ratio. And then I did know somebody in Virginia who was a personal trainer, and instead of trying to make the person lose weight and just lose weight and only lose weight, what they did is they measured the width of their shoulders. When they got a new client in, they said, okay, we're going to get your body down to perfect size. They would measure the width of their shoulders and their waist measurement. And what they wanted was to divide them and get 1.6 ratio. So not only would they prescribe dieting, but they would also prescribe working out. And they wanted to make their shoulders more broad and their waist more thin. And the ratio that they were trying to shoot for would be this golden ratio. So it's used in our bodies. It's used in Roman beautiful architecture, a lot of architecture. If you take the long side, divide it by the short side, they would build them specifically because it was more pleasing to the eye in the ratio, in the golden ratio. So it's pretty awesome. Really love it. Okay, so the golden rectangle is a rectangle whose long side is 1.62 times as long as its short side. That's known as the golden ratio. Alternate names include the golden mean, the golden section, and the divine proportion. It is an irrational number. It never ends, but it's approximately 1.6 or 8 divided by 5. All right, so suppose, this is just a little question. Suppose the line segment is divided in according to the golden ratio, if the length of the longer piece labeled L, big L, is 5 centimeters, how long is the entire segment? So let's see, right here, I'm going to go back to our notes so we can write this out. I think we're right here. So we have the same idea as what we were shown above in a slide a few slides ago. So you have this line segment. It's divided according to the golden ratio, so we'll just make a division there. Longer piece L is 5 centimeters. How long is the entire line segment? So if the longer piece is 5, then I'm just going to make a little X for the shorter piece so we can check that and see what the shorter piece is. Now, what we know for sure is the longer piece divided by the shorter piece is equal to 1.62. I'm just going to do 1.62. It's kind of bugging me because it was the two lengths were about the same. That's obnoxious. All right, so what you would do to solve this is you would times both sides by x, and then you would have x times 1.62 is equal to 5, and then divide by 1.62. Forevermore, and on the homework, what I do when I'm set up with this scenario is I just switch the x with the 1.62. And that's not really a shortcut because you're actually doing what you mean to do, but solve for x, you end up with x equals 5 over 1.62, right? So anyway, if you switch these two, when 5 over x is equal to 1.62, and you switch them, then you've got your division, what you'll put in your calculator automatically there. So 5 divide 1.62 is 3.086. All right. So this has to be 3.086. And what we were asked to do is find the length of the entire segment. So we would add those together. 5 plus 3 is 8.086. And that's in centimeters? Now, I think in your homework it asks you in the majority of the time to just round to the nearest tenth. So it would be 8.1 rounded. Right? So that's how you would do these type of problems. They're pretty cool. The next one says the sides of a rectangle are given. So you have one 9.6 and one side that is 6. Compute the ratio of the long side to the short side for the rectangle. Is the rectangle a golden rectangle? So you would take 9.6 and divide by 6 because you always just take the longer length and divide by the shorter length. And I always have a hard time with that glare on my calculator. So 9.6 divided by 6 is indeed 1.6, isn't it? It's equal to 1.6. And that is very close to the golden rectangle. It's very, very close to 1.62. So I would say yes, it is a golden rectangle. Because it's precisely, not exactly, but pretty close. All right. The next one, the length of one side of a golden rectangle is 7.7 meters. Find the length of the other side. Notice that the other side could be either longer or shorter than the given side, and use the approximation for the golden rectangle 1.62 for your work. So you have two cases. All right. In both cases, you have a rectangle. It doesn't state which of the two sides the 7.7 meters is. It could be this longer side, or it could be the shorter side. So we're going to compute both sides as though either of them could be the 7.7 side. So this side is the longer side. So we're going to give the shorter side an x so we can solve for it. And we know that the ratio of the long to short is 1.62. So we would take 7.7 and divide x because 7.7 is on the long side first. And that's 1.62. And this is the case where we have the x on the denominator, so we just switch to solve. So that means x is equal to 7.7 over 1.62. All right, and on our calculator, minus the glare, all right, we would have 7.7 divide 1.62, and that is 4.75, approximately 4.8, we'll say. Is this meters? Yep, meters. So that's if the short side was unknown. So the short side would be 4.8 if the long side were 7.7 and you were trying to make your rectangle in the golden rectangle. So the other one is the long side. So we would take x and divide by 7.7 because it's always long divide short. And that's going to be equal to 1.62, the golden ratio. All right, so this time we're going to multiply 7.7 by both sides in order to solve. And that is x equals 1.62 times 7.7, and that's 12.5 meters. All right, and that's how you would do that type of problem. Trying to see if there was anything else. Oh yeah, there's one more slide. I'm just going to stay here, save time. So consider the following household items with the given dimensions and which item comes closest to having the proportions of a golden ratio. So these are all popular things that we've seen or that we might have or use. One of them is a standard sheet of paper, and it is always 8.5 by 11. So what we're going to do is we're going to divide the longer by the shorter side and then determine if how close it is to 1.62. So if we have 11 inches divided by 8.5 inches, so remember 11 is longer, so it will be on top. That would be 1.3. I don't think that's very close. Not so close to 1.6. 8 by 10 means 10 divide 8, and that is 1.25, which is also 1.3, not very close either. So the paper and the 8 by 10 picture frame are not very pleasing to the eye so far. Let's look at the TV. My guess is people are going to want to sell TV, so it's probably going to be the closest. 16 divide 9, right? 16 by 9 ratio of width to height. Ooh, 1.8. I don't know. This is, okay, so 1.62 is the golden ratio. This is 0.32 off. These two are 0.32 off, but this one is 0.18 off. So it's the closest of the three. All right. Okay. The rest of it, the Fibonacci sequence stuff I had on the notes, I'm not going to go through because it's not really represented on the homework or on anything. So it's really great for you to go and research it if you want. But otherwise, good luck with the homework. That's 11B and 11C videos ready to go. All right.